Okay, so the new topic we're going to talk about today is called molar volume. It's going to tie in with something we talked about quite a long time ago in terms of molar mass, and it kind of ties into something that we've already done in terms of law of combining volumes. But let's get going. I'll show you what I mean. So we're going to start today with a quick recap of the law of combining volumes. That was back from Tuesday. It's not in your notebook or anything, but I just want to show you another problem, and I want to work with it just so you can see what we were doing on Tuesday once again. Then I'm going to introduce the concept of molar volume. We're going to recall how to find molar mass. We'll do a couple examples, and then we'll get some practice. Anyway, let's get going. So first of all, law of combining volumes. This is the stuff we learned back on Tuesday. Here's an example right out the gates. Just follow along. I'll show you kind of how to do this. Think as we go through it, of course. Carbon monoxide can react with oxygen gas to create carbon dioxide. How much oxygen would be needed to convert 250 liters of carbon monoxide into carbon dioxide? Well, hopefully what you remember from these questions from before is in order to do them, we have to have a balanced chemical formula. So if you read it carefully, you can see that this is going to be a formation reaction between carbon monoxide and oxygen gas, and that it's creating carbon dioxide. So carbon monoxide is a formula of CO. And it's going to be combining with oxygen gas, which hopefully you remember it's part of Hofbrinkel. Hofbrinkel are those weird elements that just don't like existing on their own. So O right there, oxygen, of course, it doesn't want to exist on its own, so it's going to be O2. And this is going to form carbon dioxide, which of course is CO2. So that's just your skeleton equation. We don't actually have any numbers in front of it yet because it's not balanced. You can see you have one carbon on both sides of the equation, but on the left side of the equation, we have 3 oxygens, and on the right side of the equation, we only have 2 oxygens. So here's something we might want to do. Maybe just so we get an even number of oxygens on this left-hand side, I'm going to throw a 2 in front of the CO. So now we have 4 oxygens on this side, and we have 2 carbons. And then if I throw a 2 in front of the CO2, we now have 2 carbons on each side, and there's 4 oxygens on each side. So this is now a balanced chemical formula. So since we're looking now for how much oxygen would be needed to convert this much carbon monoxide, let's allocate that 250 liters is actually tied to this CO right here. And since 250 liters is 2 amounts of CO, carbon monoxide, sorry, that's 2 amounts, then that means 1 amount for oxygen is going to be half of this amount. So half of 250 liters is 125 liters. And that is going to be our answer for how much oxygen gas would be needed to turn 250 liters of CO into CO2, right? Anyway, moving on. So the new concept for today is called molar volume. This is in your note package, although the first little paragraph isn't, but from this paragraph down here onwards, it certainly is. But what I want you to notice before we begin is notice that in the combined gas law, that's this guy right here, notice that in the combined gas law that we've learned before, the number of moles of gas you have hasn't mattered for predicting pressure, volume, or temperature. The implication of this is because 1 mole of any gas at a given temperature and pressure has the same volume, it's convenient to know this volume for commonly used conditions. So in other words, if you had 1 mole of a gas, doesn't matter if the gas was carbon dioxide or if it was oxygen gas or if it was nitrogen gas or whatever, 1 mole of that gas is going to occupy the same volume no matter what, as long as your temperature and pressure, of course, are held steady. So that volume is not going to change. Under STP conditions, that's standard temperature and pressure, which remember is 0 degrees Celsius and a pressure of 101.325 kilopascals. Under standard temperature and pressure, 1 mole of any gas occupies 22.4 liters. So notice the unit on this is liters per mole. That means 22.4 liters are occupied per mole, right? Now for SATP conditions, remember that standard ambient temperature and pressure, which is 25 degrees Celsius and 100 kilopascals, the molar volume is a little bit different. 1 mole of any gas occupies only 24.8 liters, right? So it's actually a little bit more than STP. I shouldn't say only. It certainly is just a little bit more, but it's still very similar. So in other words, what I'm trying to get at here is under standard temperature and pressure, your gas, no matter what kind of gas it is, occupies 22.4 liters with 1 mole, of course. And under SATP conditions, it occupies 24.8 liters. Now, if you had more than 1 mole you're going to have to use that to multiply this, right? So in other words, if you had 2 moles of a gas at STP conditions, it's going to be double this. So you're going to go 22.4 times 2. Or if you had 5 moles, you'd have to times it by 5 and so on, right? It all comes down to how many moles you have, but for 1 mole, the volume that it occupies is going to remain constant. All right, so the molar volume of a gas is the same volume occupied by 1 mole at specified temperature and pressure, just like we said. All are at standard temperature and pressure, STP. This volume is 22.4 liters for all gases, and at standard ambient temperature and pressure, the volume is 24.8 liters. So I don't know how well you can see this balloon picture right here. It's kind of small even on my screen. I can only imagine on the projector. But what it shows is this balloon on the far left has helium in it. This one has oxygen in it. And then this green one has nitrogen in it. Now, helium, oxygen, and nitrogen on the periodic table are all going to have different amounts of molar mass, right? So 1 mole of each of these is going to have a different amount of mass to it. But what I want to make very clear is, since all of these balloons are filled with 1 mole of gas, you're going to notice here that all of them have the exact same volume. And it looks to me, with a temperature of 273 Kelvin and 1 atmosphere, that this is under STP conditions. So it would be 22.4 liters is how much gas is in each of these balloons. So even though each of these balloons is filled with a different chemical, they still will occupy the same general volume. But the one key difference for sure is that the mass of each of these balloons are going to be different. Helium only has a mass of 4.0 grams. Oxygen has a mass of 32.0 grams, so quite a lot more than the helium balloon. And nitrogen has a mass of 28.0 grams, right? So in other words, these 2 balloons are going to weigh a lot more than the helium balloon would. And that's a big part, of course, of why we use helium for balloons. It's much lighter and it'll float a lot easier. Anyway, moving on. So another thing I want you to recall is finding the molar mass. Now, I want you to remember that on the periodic table, the molar mass of each element is given as the number given to 2 decimal places. I'm pretty sure on your periodic table, it's kind of lodged up in the top right-hand corner for every element. I could be mistaken, but again, you're looking for the number that's written to 2 decimal places. So what the molar mass tells you is it's how many grams 1 mole of that element weighs, right? So oxygen, for instance, I know that one off the top of my head is 16.00. What that means is 1 mole of oxygen, just plain oxygen, not even O2, just plain oxygen. 1 mole of oxygen is going to have a mass of 16 grams. So 16 grams per 1 mole, or in other words, 16 grams per mole, right? So thus, the formula for molar mass can be considered molar mass, which is grams per mole, is equal to mass in grams, divided by moles, which are, of course, in moles, right? So the unit on molar mass itself, grams per mole, tells you what the formula is. It's grams over moles. Now, the molar mass of a compound, so not just one element, but several elements all jammed together, is actually the sum of the molar masses of all the elements that make up the compound. It's important to remember, if you have more than one of a certain element in there, like you would for, like, say, CO2, you're going to take the molar mass of carbon, add it to the molar mass of oxygen, but you're going to multiply that oxygen's molar mass by 2 because there's 2 oxygen in CO2. All right, that's kind of enough me blabbering on again today. So we're going to do a few examples. This one's not in your data booklet. This is just an example dealing with molar mass, not even with the molar volume stuff we've done. What I want to ask you, this is something I would have asked you a few weeks ago as well when we first learned this, is find the mass of 5.00 moles of mercury 2 oxide. And that's what that picture is right there. It's basically like the chemistry version of the forbidden Cheetos. Right? You don't eat that. That's what I'm all saying, right? It looks like Cheetos, but that's no bueno, right? You don't want to be touching that. Anyway, what I want you to do, though, is I want you to find the mass of 5 moles of mercury 2 oxide. So use your data booklet, use your periodic table, give this one a try, and remember the molar mass is given as grams per mole, and that helps you figure out what the formula is that you'll be using. Anyway, pause the video here, give this one a try. All right, I'm going to go over this one. So what I like doing first is I kind of like taking inventory of what I got. Well, we know how many moles we have. It's 5 moles. So I'll say n, lowercase n, that's just what I use for moles, is 5.00 moles, right? So that's how many moles of something that we have. Now, the next thing I got to take note of is we don't really have much of anything else. So we know that we're dealing with mercury 2 oxide at very least. This 2 here in Roman numerals, of course, means that mercury has a positive 2 charge. It's a multivalent element, which means it has more than one possible charge. The formula is nice, or rather the the written out word equation on this one is nice because it tells us what the charge is. It's mercury 2. So 2 plus is what our charge is on mercury. Oxygen, on the other hand, always has a 2 negative charge when it's in an ionic compound. So we know the formula for mercury 2 oxide is mercury, which is Hg, and oxygen, which is just O. So HgO. Now this actually helps us find our molar mass. Like I mentioned before, if you look on your periodic table, you can see the molar mass of mercury and the molar mass of oxygen. And you just add them together to find the molar mass of mercury 2 oxide. So molar mass, I like representing with a big capital M. The molar mass of mercury is 200.59 plus the molar mass of oxygen, which is 16.00. So the molar mass of HgO, mercury 2 oxide, is going to be 216.59, and the units on that are grams per mole. All right. What we're looking for, however, in this question, like this is a nice enough bank we've got made up right here, what we're looking for is the mass. So we're going to look for how many grams we have, and I use a lowercase m to represent that. Now, like I mentioned before, your units on molar mass kind of give you a hint as to what the formula for molar mass is. So we'll say the formula for molar mass, capital M, which is grams per mole, equals your number of grams, so lowercase m, over your number of moles, so lowercase n. So let's throw in the numbers we've got here. That means 216.59 equals, we don't know our mass, so I'll leave that as lowercase m, but we do know the number of moles we have, it's just 5.00. So to find this lowercase m, we just need to multiply by 5 on both sides of the equation. So what this gives us is our mass, lowercase m, equals 1,082.95 grams. Well, that's a nice exact answer, but notice in science, remember what I told you before, you got to watch your significant digits. This question only has 3 significant digits, so we have to round to only 3 places. That means we could express our answer using scientific notation with just keeping these 3 digits, so 1.08 times 10 to the 123, and that is still in grams. However, an alternative is notice that in 1 kilogram, there's 1,000 grams, so you could actually say your mass in this case is actually 1.08, and instead of 10 times 10 to the 3 grams, you could just say kilograms. So both of those answers are just fine. Both of them are 3 sig digs. You get your point across one way or another. So bottom line is 5 moles of mercury 2 oxide is going to have a mass of about 1.08 kilograms. Anyway, moving on to molar mass questions. Here we go. So this is in your data booklet. This one really actually is. I'm going to walk you through this one because we haven't done any questions like this before. How many moles of gas would be contained in 55.7 liters at STP and SATP? So what I want to remind you is the type of gas we're working with doesn't actually matter. So in other words, the volume of a gas is going to be the same no matter what kind of gas it is. It just depends on how many moles of that gas you have, and that's what we're looking for in this case. Let's start with STP conditions. You might remember from earlier in this lesson, I mentioned that the molar volume, so in other words, the volume of 1 mole of any gas at STP conditions, which is 0 degrees Celsius and a pressure of 101.325 kilopascals, the molar volume of that is going to be 22.4 liters per mole, right? This is how much liters 1 mole of a gas should occupy. Notice we actually have 55.7 liters. So what we have to say is 22.4 liters per mole equals some amount of liters, that would be 55.7, over some amount of moles. I'll say it again. This is in liters per mole. Just like before with our grams per mole formula for molar mass, our molar volume can be thought of the same way. It should be some amount of liters over some amount of moles. If we're looking for the sum amount of moles, we just need to multiply by n on both sides. So we have n times 22.4 equals 55.7. And then, of course, to get n totally by itself, we just need to divide by 22.4 on both sides. 55.7 divided by 22.4 is actually going to give you, rounded to 3 sig digs, 2.49, and the units on that are going to be moles. So under STP conditions, 55.7 liters of a gas is actually 2.49 moles, so almost 2.5 moles of gas. Now let's look at SATP conditions. SATP conditions have a slightly different molar volume. The molar volume was 24.8 liters per mole. Now, just in case you're wondering, because I guarantee some of you guys are wondering this right now, and I should have mentioned it earlier, you will not be expected to memorize these two numbers. Don't you worry. We're going to include them on any quizzes or exams that we give you. But again, you'll be working with them so much you'll hopefully have them memorized before we even get there. Anyway, back to this one as well. 24.8 liters per mole tells you how many liters 1 mole of gas occupies at SATP conditions. That's 25 degrees Celsius and 100 kilopascals of pressure. But we know we have this 55.7 liters instead. So just like before, let's set it up using our units. 24.8 liters per mole should equal some amount of liters, that'd be 55.7, over some amount of moles, which we'll call N. So this is solved the exact same way as the one before. Multiply by N on both sides to get N times 24.8 equals 55.7, and then divide by 24.8 on both sides, and you're going to find that your number of moles to 3 sig digs is 2.25 moles. So, moral of the story in this case is under SATP, you're only going to have a smaller amount of actual moles of substance. So an actual physically smaller amount of substance is going to take up a larger volume than an equivalent amount would have been at STP, right? So that's another way of kind of interpreting and thinking of this one. All right, example 2. Let me see if this is one I want you guys to do on your own. 1 second here. You know what? Just for fun, let's see if you guys can do this one on your own. This is going to combine molar mass with molar volume. Notice I'm only giving you the amount of grams of carbon dioxide, and we're looking for the volume at SATP. So I'm going to give you a hint right off the bat. You're going to want to use this amount of grams and the fact that we're dealing with carbon dioxide to find the number of moles you have first. But ultimately, we're looking for what volume of gas we need. Pause the video here, give yourself a couple minutes. I'll go over it in just a second. Okay, so that one was challenging. Hopefully some of you were able to get it, but if you weren't able to get it, don't kick yourself too hard here. Let's first focus on what we got. Before I find the number of moles here, I want to just acknowledge that since we know this is at SATP, we're going to have a molar volume of 24.8 liters per mole, right? So in other words, if this turns out to be just 1 mole of carbon dioxide, then we know our liters is going to be 24.8 liters because there's 24.8 liters per mole of gas at SATP conditions, regardless of what kind of gas it is, carbon dioxide, oxygen, nitrogen, whatever, right? So what we should do then is, since we know our molar volume and we're looking for an amount of liters, we should figure out an amount of moles we have so that we can find that missing piece. Okay, so 112 grams of carbon dioxide. Let's first figure out what our molar mass is of carbon dioxide. Carbon dioxide is CO2, so that means we have 1 carbon, 2 oxygens. The molar mass of carbon is 12.01, plus the molar mass of oxygen is 16.00, but you're going to need to multiply that by 2 because there's 2 of them in there. So 12.01 plus 2 times 16 is actually going to give you 44.01 grams per mole. That's the molar mass of carbon dioxide. We'd like to know how many moles of carbon dioxide we have. Well, notice this. Since we have 44.01 grams per mole, we can say that this is equal to some amount of grams, which is 112, over some amount of moles, which we'll just call N because it's unknown. That's a terrible N. That looks like an H. There we go. That's a better N. So we don't know how many moles we have. We need to figure that one out. So once again, let's times by N on both sides. So N times 44.01 equals 112, and then divide by 44.01, and you're going to find that N is equal to 2.544876, and then some more stuff, moles. The reason I didn't round this is because we're not done yet. We should keep as many decimal places as reasonably possible so that we're not rounding until the very end here. Anyway, so we know our number of moles now. Let's go back to this idea of molar volume, because ultimately we're trying to figure out volume here. So if we take this and look back at our molar volume, we know our molar volume is 24.8 liters per mole. So we should set this as some amount of liters. How about I just call it V for volume over some amount of moles, which we know now. It's 2.544876 moles. Whew. So if I times by this crazy weird decimal number of moles, that's going to cross moles out on this side, and it's going to tell us just how many liters we have of volume. So our volume now is 24.8 times 2.544876, and I'll round that to 3 sig digs, so it's 63.3 0.1 liters, which shouldn't be a big surprise because again, it's like we have about 2.5 moles. We know 1 mole is 24.8 liters. So you just times that by about 2.5, and that's where you get. All right. That one was crazy, don't worry. Hopefully it'll come to you a little bit later. Just get the idea down that moles are what connect your molar mass to your molar volume. And just look at the units inside your molar volume. It's liters over moles. So that's what you got to use for your units when you're calculating things, right? So it's like the formula is built in. It's right given to you, okay? All right, example 3. This one's a lot different than the other ones, but don't panic. If you know what to do, this one will take you literally no more than about 20 seconds. So I am going to get you guys to give this one a try. What would be the molar volume on Mars be? Ooh, that's weird. What would be the molar volume on Mars be? Whatever. What would be the molar volume on Mars? Yeah, if 3.50 moles of gas has a volume of 9,608 liters. So what we're pretty much asking here is what are your liters per mole? Just like it was 24.8 liters per mole at SATP, we don't have SATP on Mars though. Mars does its own thing. It's got its own temperature and pressure. Try to find that molar volume. I'll give you a hint. It's going to be a pretty big number. Pause the video here. Give it a try. All right. Hopefully you were able to get this. If you weren't able to get it, you can watch as I do this and you'll go, oh, really? It was that simple, huh? Well, remember what I said. Molar volume is liters per mole. Notice we know how many liters of gas we have. Notice we know how many moles of gas we have. It's just liters per mole. So in other words, 9,608 liters divided by 3.50 moles. Liters over moles. We want it as a unit rate though. We don't want it over 3.50 moles. We want 1 on the bottom. So let's actually divide these. 9,608 divided by 3.50 actually gives us 2,745 liters per mole, which is awesome. That's a great exact answer. But just because life needs to be more difficult than that, notice for whatever crazy reason, we only gave you 3 sig digs. That means we need to round this to 3 sig digs. So this is going to become 2.75 technically, because that'll round it up to a 5. 2.75 times 10 to the 1, 2, 3, so 10 to the 3 liters per mole. That right there is your molar volume, at least on Mars, right? So not under SATP conditions, not under STP conditions. That's under Mars conditions, whatever the temperature and pressure on Mars is. Both of those are really low, very low temperature, very low pressure. Whew, all right, anyway, that was quite a long lesson. I wasn't expecting it to be that long today. I apologize, but for practice, what I want you to do is work on any of the molar volume practice questions in your notes booklet first, and then we have a worksheet. One side of it is titled the Combined Gas Law Worksheet. It's just the stuff that we covered I think it was actually last week that we first covered it. But the second side of that worksheet, the back side of it, might be more interesting to you. It's on molar volume, and I want to give you a heads up. Please just do the even questions. You don't need to worry about the odd questions on that one. So again, note booklet, do those first, and then try the worksheet. Worksheet should be handed out to everyone anyway, just so you have it on hand, but focus on that note booklet first. Anyway, if you have any questions, I can take them at a future time when I return. Best of luck.